Hi, we're here to present JoeRank, a scientific paper influential index. I am Jie Li.
I'm Yutao.
So, with the rapid development of artificial intelligence and general computer science, there's a tremendous growth of scientific publications in the recent years. It has become very difficult and even more difficult over the years for researchers to keep up with the trend of scientific literatures even in their own field, let alone the bigger scientific community. So in order to overcome this information overload problem, we attempt to extract several useful insights from scientific papers. We use the interactive data science approach to visualize the large number of papers and authors in the field of modern computer science, specifically papers and authors in the field of information retrieval, machine learning, web services, data mining, and so on. So first of all, let me describe the data source we use. Our data is from two sources. First of all is Web of Science. Web of Science is a comprehensive citation search engine. It has access to multiple databases that reference cross-disciplinary research, which allows for in-depth exploration of specialized subfields within an academic or scientific discipline. We use WOS services to retrieve paper citation information for artificial intelligence papers from 6,655 research institutes around the world from year 1980 to the present. For each research institute, WOS has a record of the aggregate number of papers it has and the aggregate times of sites it receives. So for example, CMU have 5,627 artificial intelligence papers ranges from the year 1980 to the present, in total receiving a number of 106,000 citations. We also retrieved the aggregated citation numbers for the countries and regions around the world for the last 3 years. For example, California alone has about 351,000 papers, receiving a total of 1.5 million citations for the last 3 years. The second source of data we use is from Aminer. Aminer is an academic paper search engine with a lot of researches, a lot of publications, a lot of citation information. Specifically, we use the citation network datasets, topic to co-author, and topic, paper, and author networks. So these two networks is published in the year 2009 with the paper Social Influence Analysis in Large-Scale Networks for the conference SIGKDD. It covers about 640 thousand authors in 8 computer science topics up to the year 2009. It's a little outdated, but we use this data network datasets to develop our new paper influential index. So the 8 computer science topics are data mining, web services, Bayesian network, web uh, mining, semantic web, machine learning, database system, and information retrieval.
Okay, so during the midterm project, we've shown the distribution of publications from different countries or institutes along with different years. So for the final project, we want to connect the co-citation data from the Web of Science as well as a minor data set to build up a bar chart and a heat map here for the large-scale general situations in the modern computer science. So, and the bubble graph and the network graph to demonstrate the co-citation among papers and scholars. So the citations, in some degree, could represent the prestigious contributions, authorities, and other important aspects of research power of certain institutes or countries. Also, it's a very important standard to show the achievement of certain papers or scholars to the modern computer science. In this project, we're going to analyze the papers published in AI domains by analyzing the citations patterns and the authors' demographics, co-authors' information, and paper importance scores. We developed an independent index called ZoRank, which draws an analogy from Google's PageRank algorithms. So first, let's focus on the large scales. So we build two graphs. One is a bar chart and another one is a heat maps. So for the bar chart, we have the data for the cumulative citations in AI along the institute from the 1980s to now. So we can see that for this University California systems and the MTI, Berkeley, and Carnegie Mellon are the most top institutes that contribute to the AI papers based on the citation numbers. And some other institutes outside the Americans, like the Nanyang Technology universities and also the University of London, are also very important contributors to the AI development. And worldwidely, you will see that USA and China are some of the top countries that contribute to the AI research development. And this data is collected from 2015 and 2018. So, but for this large-scale data, we find that it's kind of less interesting to demonstrate like how the contributions distributed among them because we don't know much in details like which papers or scholars contribute most interesting stuff to this development and of the research in the AI or the modern computer science. So we should focus more on the details of individual papers or individual scholars. So further, we build up two network visualizations. One is about the citations in the information retrieval, and also the other one is co-author networks about the huge 400 authors, like about the web services development. So for the network about the paper's citations, user will notice that the paper, this one, the real-life information retrieval, a study of user queries on the web in the information retrieval. Now this one has the biggest size in the graph of the node. And also this paper, like the perceptual speed learning and information retrieval performance, as well as this one, like applying formatic characteristic of database. Then this one has the biggest node, but these two papers, they might have more linkage than the other papers. Also shows the importance of this paper in this field. And they are cited by many other papers because they have some information or knowledge that the other papers are based on. So beside this, we have the features of the, which is the big, the size is big. That means that you have some absolute citation account is big. And also that the nodes that have many outside linkage, which shows that this is needed for other papers. How about we can add some further features and which is more comprehensive to show that this paper is not only important in that its citation number is big, but also its linkage is also many. So we're gonna introduce a new feature which is more comprehensive in the later part to show depths, show more depths in our in depths. And for the co-author networks, you'll find that, which is similar to the pretty paper network, that it has like for example the vendor artist and this node, the Jian Yang. You'll find the paper the authors whose head node is the biggest size and also with some massive linkage outside of it. So these are the most important contributors to the websites, and you can explore this graph by yourself.
Okay, so to solve the problem Yuntao just mentioned, basically incorporating the node size and the number of linkage to the nodes, we propose a new feature index to measure paper importance. From A minor, we get the absolute citation numbers for each paper with the citation information, i.e. which papers cited each paper. For the paper network and author network above, it is hard to get a direct feeling of which paper or which author is the most important in a given computer science topic, because besides the node size and the number of linkages, there's no objective or no intuitive way to show which papers stand out. So we need a new feature that can reflect this importance of paper and author. We could simply use the absolute citation to form bar chart or bubble chart or network force-directed network like before. But we want to dig more into the raw data. We find that just using absolute citation cannot send out enough signal to decide which paper is important. The logic is that absolute citation number may not be salient enough to reflect the importance of the paper. So for example, the lesser important paper judged by the citation number alone may be cited by a more important paper with much higher citation numbers. In that case, this seemingly less important paper actually serves as a jumping board or the inspiration for a more important paper. Based on this observation, we take analogy from the Google PageRank algorithm and propose JoRank score for the paper. Two authors happen to share the same last name, so we name it JoRank. So PageRank, according to Google, works by counting the number of quality of links to a page to determine a rough estimate of how important the website is. The underlying assumption is that more important websites are likely to receive more links from other websites. Here, intuitively, we think that citation number alone may not reflect the originality or the true contribution of the paper. So if the paper that cited this paper have a very, very high combined citation numbers, then we are more sure that this paper has more importance. So the paper does not have to have a large citation number by itself, but the paper that cited this paper, if they have a large combined citation number, then this indirectly reflects that this original paper are more important. Technically, we made an n by n paper citation matrix C. If paper J cites paper I, then Cij equals 1, otherwise 0. We also made an n by 1 absolute citation number vector A. If paper I received X citations, then AI equals X. Then we multiply C by A and get an n by 1 JoRank vector Z. The Zi here in the reflects the JoRank score for paper I. We present JoRank bubble plot for papers in 3 different fields: machine learning, natural language system, and data mining. So the first bubble plot you can see here, each bubble is title for the paper. It's in the machine learning papers. From our diagram, you can see here this paper, Belief Network, Hidden Markov Model, and Markov Random Fields, a unifying view, has a high score of 1,267 JoRank score. But in actuality, it only has about 138 citations. So that means it is more important in our system, which considers the linkage to the node, besides the size of node. In some other cases, like the strength of weak learnability, PaperRank gave it about 800 points. But in actuality, till the year 2009, this paper has not received much citations. But with the boom of artificial intelligence in recent years, since 2010, it received over 4,000 citations. So in some way, our JoRank score, back using the data up to 2009, predicts the rising star, the rising status of this paper in the future by giving it a high rank. This paper, Probabilistic Independence Network for Hidden Markov Probability Models, has about over 1,500 JoRank score, and it also has a large number of citations, as written in the report. Similar things can be shown for papers in natural language systems, where you can see papers like Introduction to Special Issue on Word Sensitive Ambiguity have a high JoRank score, but at the time, it probably does not have so many citations. If you are interested, you can search for each paper and compare the current citation number, the citation number back in 2009, and with our scheme. We believe that our index JoRank score is meaningful because since we rank some paper with not so many citations, but serve as a jumping board or inspiration for other highly cited papers, it can predict which paper is the jumping board or the cornerstone for other more exciting, more highly cited papers. And also it can predict a future rising star. We definitely need more thorough tests to validate our assumptions, but the results shown here in some way reflects the effectiveness of GeoRank. Next, Yingtao will talk about the data 4C for our data sets.
So I'm going to talk about the 4C about our data set. First of all, I'm going to remind you of the structure of our co-citation data set, which is more interesting data set. So one of the is about the vertices information contains a name, which is the paper titles or score name of the vertices, and then the absolute citation count. The other one is about the linking age among the vertices within the certain group of categories. It gives the index of the two ends of age and the constant one for showing that there's a linkage between these two vertices. And this is always going to be 1. So for the first part, the completeness. So as the structure shown above, the data is very complete. There's no missing data or any components found in that data during the cleaning data processes. So all the vertices in the dataset have at least one linkage connected to other vertices. There's no isolated ident in our dataset, which is also meaningless in our cases. So the only problem is whether there are some important papers that are not included in our pool. But the dataset surely only focuses on the papers written in English, so the nature of the dataset makes us can only do some research on the English written papers in the modern computer science. For the coherence, there's no mismatches on the data type of any components in our dataset. The name part has all the data being text type, and all the citations are integers. There's no floats involved because the citation cannot be floats. And the linkage index are within the range of the min and the max of the vertices index. So all data we connected for co-citations make sense to itself. For the correctness, the co-citation data are simple records of the citations. So there's barely human factors that will interfere with the data qualities or introduce any bias on the data we connected. There might be some selection biases that interest in the dataset that those connected datasets are the most salient ones. But it won't hurt anything because our goal is to find out the most salient contributors to the modern computer science. All we care about are the top several hundreds of interests in our pool, and we care less about the distribution of the data, and so we care more about the ranking of the data. This is good for our research goals. And for the accountabilities, the dataset is accessible to all the public and for the research purpose. And it also has some version controls on their database. But we basically can only access to its most updated dataset from their offered link. And also, the data from the miner stopped being updated since 2009. And in the future, if there's some necessity of updating our analysis on this dataset, we might need to apply our model or analysis algorithms on some more updated dataset about this co-citations. And thank you. This is all the content for our presentation.